So, yeah, you'll see that I only started this last section.
Okay.
Um,
All right, so I'll take a look at what you have here. Let's see. Okay, that's good as far as it goes, but I think you could draw even one more resonance structure.
hmm, okay, let me see. Okay.
Okay, there's a mistake in that last picture that you drew.
Oh, yeah, I didn't write that positive.
All right, and remember that's important. The most important factor is to get those charges. How do we know that charge is not changing?
Um, it is both receiving and losing electrons. It's in the middle of the chain of
Yeah,
arrows.
nothing in the middle has its charge change. Okay, notice that I noticed that off to the side you said carbons 1 through 4 could be basic or nucleophilic, but actually
Yeah,
you hadn't really proven why carbon 4 could be nucleophilic yet. It wasn't until that last picture that we showed. So this is actually kind of unusual or weird. Every single carbon gets a negative charge in one of the resonance structures. The negative charge goes all the way around the ring. Why did you stop where you did? It might be because you thought you had finished the cycle. But notice that when, because the negative charge had kind of gone all the way around the ring, but it didn't end up in the same place when you went all the way around the ring. And so it turned out it can kind of go around the ring multiple times. This is kind of a trickier case than some of the examples we saw before. So it turns out the negative charge could end up on any of the carbons. Kind of a weird case. So
yeah.
any of them might be nucleophilic or basic. And you said the nitrogen might be acidic. Yeah, because it does have, it's more acidic than normal nitrogen would be because it has resonance structures with a positive charge. That's a good point. Okay, good. Yeah, so I think that would be the reactivity we would expect there. Okay,
Okay.
so okay, so actually we didn't quite 100% get that one correct because the job was to write all the resonance structures and we had left one out. That was a tricky one to draw all of them. All right, so I'll take a look at the next example. Okay, so which carbons do you predict would be nucleophilic?
Carbons 3 and 4,
Why is carbon 3 nucleophilic?
because of the negative charge in one of the resonance structures.
Point to that. Great. And which is the other carbon that's nucleophilic?
Oh, I'm sorry, I wrote the wrong number. That is 5.
Okay, good. That might have happened because you didn't keep copying the numbers into the other pictures. So we've
Yeah.
seen that it's often a good idea to number all the pictures. So by putting in those numbers, it was easier to apply them. All right, so 3 and 5 are nucleophilic and basic. Let's see. Carbon 1 is electrophilic. That's a fair, all right, that's a fair point.
Maybe more so than carbon-2. I said carbon-2 could be electrophilic, but it seems less likely.
And why is that?
Because while it does have an oxygen with a positive charge next to it, in some resonance structures, it also has a negative charge on the opposite side.
That's a good point. So probably we should erase that one. The negative, it's just as close to a negative as it is to a positive. So it probably would not be electrophilic. That's a good point. It's just as close to a negative as to a positive, so it probably would not be electrophilic. Okay. Now you said the oxygen would be acidic. Now, what's the definition of an acid?
It would donate a proton to receive electrons.
Okay. Now notice this oxygen doesn't have any protons.
Right.
So it couldn't be a normal acid. I suppose it could be kind of a weird Lewis acid, but that would be kind of an unusual case. So we should probably erase the acidic for the oxygen. It wouldn't be the normal type of acid we think of in organic chemistry because it doesn't have any protons to donate. Okay. All right. Now, in actuality, what's most likely to happen here is 3 or 5 would be nucleophilic. What would actually happen in the reactions you would see would be 3 or 5 would be nucleophilic. But theoretically, we could also see carbon-1 as an electrophile. That makes sense in theory, but what you would actually see would be 3 or 5 being nucleophilic. Now, there were some more questions on that set that you hadn't done before, so let's just take a look at those, if you've had a chance to do those now. Okay.
Yeah, I think that it was...
I think you'll have to go pretty close to the start.
I think right here is where we were left off, where I had with that benzene ring and
Okay, so this next example had lots of resonance structures, but I think you succeeded in drawing all of them. So that's good.
good.
In the first resonance structure, why did you move the electrons towards the oxygen in the carbonyl instead of moving them towards the carbon in the carbonyl?
Because of the electronegativity in oxygen. It has more electronegativity, so it would the electrons would move towards oxygen.
Okay, good. Okay, now the next example, I think we can draw another resonance structure.
Oh, okay.
See if you can find that next structure.
Perhaps something like that. If that works. No, that doesn't work. Okay. I'm not sure where to go with that. It seems like Okay.
Okay. Well, that was good. That you had some trouble with that, but you kept thinking about it until you figured it out. Now that you have it drawn, we should be able to see that actually this next set of arrows was very similar to the first one. Do you remember that the way we originally learned resonance was by learning like 6 different patterns? Now at this point you might be comfortable enough that you might not be thinking about the patterns explicitly, but if you get stuck you might want to go back to those patterns. What was the patterns you used with your first set of arrows? Well, your first set of arrows were based on the pattern of a lone pair on an atom that's connected to an atom with a pi bond. The first set of arrows were a lone pair on atom 2 that's connected to atom 3 that has a pi bond. But that pattern occurred again on the right side of the molecule with the second resonance structure. In the second picture, you had the lone pair on carbon 4, and that's connected to carbon 5, which has a pi bond. So you could use that same pattern over again. Now, you might have had more difficulty seeing that because we haven't done much resonance with triple bonds before. We haven't worked too much with triple bonds before, but it follows the same pattern as the examples we saw previously. We haven't seen many examples in the past where we ended up with 2 double bonds right next to each other. But in any case, this still followed the same pattern as before, and it doesn't break any rules. Okay, so that's another resonance structure. All right, so now we'll take a look at the next example. You might want to mark that one since we did. The goal here was to draw all the resonance structures, so we got that one incorrect since we left one out originally. I'll take a look at the next example.
Okay.
Did you think about the reactivity for these molecules?
No, I wasn't quite thinking of that.
Okay. Well, in any case, I don't want to spend more time on that. So some of these are kind of complicated. So it might be a good exercise to think about the reactivity here, but some of these are kind of complicated. So we'll just focus on drawing the resonance correctly here. Let's see.
Okay.
All right, the next example looks correct. Okay, in this one it was important to know where to stop. So it doesn't. You drew as many resonance structures here as seem reasonable. There aren't any more that involve the nitrogen on the far left, I don't think. Let's see. Yeah, there aren't really any. There's no significant resonance structures that involve the nitrogen on the far left, so that's good. Okay, I'll look at the next example. All right, that example seems fine as well. So let's look at the next one with the nitrogen. This next example is good. This next example is a little bit unusual because most of the time when we saw that problem in the past, I would have started by giving you the structure on the far right, the neutral structure. Normally you're given the neutral structure and you have to discover the hidden charges. In this case, you were given the one with the charges. Which of these resonance structures is kind of the most preferred? It's the one on the far right because it's neutral. In this case, you started with the resonance structure that was kind of somewhat less significant, and you had to draw the other ones, including the best structure, which is neutral. All of them are worth drawing, however. Some of them, the ones with charges, are less significant, but they're still very important because they show us the hidden charges. Okay, so in any case, you got that one correct. Good. So I'll look at the next. Okay, that's good for the next example as well. That next example is a good example of how the beta carbon next to a carbonyl has a hidden positive charge. That's something we've talked about in the past. So let's look at the next example. Okay, fine for that. So I'll take a look at the next one with the nitrogen. Okay, One thing we've had a little trouble with in the past, do you remember we've seen that when there's a neutral atom at the beginning of the string of arrows, students often forget to change it to positive.
Yeah.
But I just wanted to point out that you did that correctly here. In many cases here, you had a neutral atom at the beginning of the arrows, but you kept changing that neutral atom to positive. You were doing that correctly, so that's good. Okay, that one's a little different from the ones we've seen before, but I think you got all the structures. I'll take a look at the next one with the nitro group. Okay, this would be tough to get all the structures. Let's see here. Okay, good. You know, I think there's actually some additional, maybe quite a few additional structures in this case, but you drew a lot, so that's good enough. You got the general idea here. This one happens to have many, many different individual resonance structures, but you did a good job at seeing some of the range of structures that you have. So that's good enough work on that.
Okay.
So in any case, yeah, so that's good. All those structures are significant. It would be tedious to draw every single possible structure there. So in any case, I'd mark that as a success. Okay. If you were focusing on reactivity, it would be easier because then you would kind of focus on the structures that help you to explain the reactivity that you're thinking about. When you're just drawing the resonance structures in the abstract, it's hard to know which ones to draw when there's so many. So I'll look at the next example. Okay, that looks fine for the next example. Were there more?
No, I don't think so. I think that was
okay. So that was kind of our summary exercise for resonance then. I think you pretty much got all of those correct. I don't think you drew any wrong resonance structures. There was only one picture there where you left out a structure. There was one picture where you left out a structure, but overall it's pretty good. Those were pretty challenging questions. Those were pretty challenging questions. So I think that shows we have a good, strong grasp of resonance here. And we ended up not practicing the reactivity part for that problem, but you've been doing a good job on those in the past. So I think we've made some good progress on how to use resonance for predicting reactivity as well. Okay, good. So I think that shows we've made some good progress on that resonance material that we worked on quite a bit.